Hello to everyone. I apologize for the delay on our part. We had some technical difficulties. My name is John Ulrich, and I'm an editor for Wiley, as well as for the journals Advanced Energy Materials and Advanced Functional Materials, as well as being the editor-in-chief of the journal Energy Technology. On behalf of Wiley, and particularly these journals, I am proud to welcome you to our virtual symposium, Create a Rechargeable World, in honor of Professor John Goodenough and to celebrate his 98th birthday. It's truly an honor that we have the opportunity to celebrate John Goodenough's birthday with him today, and it is a privilege that I get to be one of the first to say, happy birthday to you, John Goodenough. And thank you so much for spending a part of your birthday with us today. Of course, I am only one of many who are gathered here virtually to celebrate Professor Goodenough's birthday. I want to say good afternoon to everyone watching from here in Europe, good morning to everyone in North and South America, and a good evening to those watching from Asia, as well as a heartfelt welcome to everyone watching from everywhere else in the world. We are also streaming the platform via Bilibili in China, and we welcome those watching on this platform as well. The idea for this symposium grew out from the dual special issues of Advanced Energy Materials and Advanced Functional Materials on the same topic, and all of the articles published to this point are accessible at the link and QR code on the right-hand side of this slide. All of the speakers at today's symposium have article contributions to these issues, along with many other leaders in the field of electrochemical energy storage. And I would particularly like to thank Professor Manthiram and Professor Yunhui Huang for their efforts as guest editors of these two issues. As you can see from the logo of Advanced Energy Materials, this is a special time for the journal, where it is celebrating its 10th anniversary this year. Please stay tuned for further activities to help celebrate this in the coming months, where of course some of our plans for in-person symposia and events are currently being adapted for virtual equivalents. Professor Goodenough played an important role in the journal's development over the past 10 years, and I looked up his most recent publications from the first issue of this year, volume 10, in January of 2020. What an impressive example for us of continued and sustained productivity and passion for science at then 97 years old at the time that the manuscript was prepared. Professor Goodenough, we look forward to receiving your next manuscript as well once it's ready. I also recognize Dr. Hadi Khani's name as the first author here, and he's helping out today with arrangements to help speak to Professor Goodenough, so thank you very much for that. I would be remiss if I didn't mention one of Wiley's newest open access journals, just being launched now, Advanced Energy and Sustainability Research, which is positioned as a sister journal of Advanced Energy Materials and Advanced Science, as a broad open access venue of high quality research on energy and sustainability. The publication fees, or APCs, will be waived throughout 2020, so it will be free to publish open access in the journal until the end of the year. Now, coming to the agenda of what we're going to talk about today. To briefly guide you through the agenda, following some last introductory remarks, we will play a 10-minute video with birthday wishes from Professor Goodenough from many around the world. Then, following an introduction from Professor Manthiram, Professor Goodenough himself would like to say a few words. Following this, we'll have the 5 scientific talks of the day from the very impressive list of speakers. A lot to look forward to. For the 5 scientific talks, you can submit the questions for the speakers via the platform's chat function, and a selection of the questions will be answered in the Q&A session following each talk. You can help us by typing the @ sign and then the speaker's last name at the beginning of your question to help us direct it. Without further ado, I would like to briefly introduce our next speaker, Professor Yunhui Huang, for a few words, and I'm sure many of you already know him for his work on lithium-ion and next-generation batteries. He worked with John B. Goodenough at the University of Texas at Austin for more than 3 years, and in 2008, he became Chair Professor of Material Science at Huazong University of Science and Technology. Professor Huang, I hand it over to you and the floor is yours.
Okay. So now it's okay. Okay. Thank you, Dr. John Ulrich. Dear Professor John Goodenough, dear all professors, colleagues, and friends. As we all know, today is Professor Goodenough's 98th birthday. We are delighted here to have an online virtual symposium organized by Wiley to celebrate his birthday and discuss the development of rechargeable batteries. Last year, Professor Goodenough won the Nobel Prize in Chemistry together with Professor Stanley Whittingham and Professor Eric Yoshino to celebrate Professor Goodenough's Nobel Prize, and in honor of him, Wiley planned to publish dual special issues in Advanced Energy Materials and Advanced Functional Materials. Professor Arumugam Manthiram and I serve as the guest edit. Many leading scientists, mainly from Professor Goodenough former students, postdocs, visiting scholars, and colleagues in the field of batteries have contributed articles, including reviews and research papers. Now the special issues are mostly online and will be finally published soon. We thank all the contributors for their contributions. In today's symposium, many professors, Professor Goodenough, former students, postdocs, and colleagues have given their best and warmest wishes to his birthday. We have received more than 40 videos, and there are still many friends wanting to express their respect to Professor Goodenough. We really appreciate them. Since today, we only have 12 minutes to play the video. Some of the videos from the former students and postdocs and the videos we received in the recent 2 days have not been included in today's video. Instead, we will combine all the rich videos in a big file and send to Professor Goodenough. In the end, here I will represent all Chinese former students, postdocs, and visiting scholars and their students to say happy birthday to Professor Goodenough. Now, please play the video. So next step to play the video. Thanks.
John, happy 98th birthday. Please enjoy, and I look forward to seeing you in person in 2 years for your 100th birthday. Enjoy.
Happy 98th birthday, John. It was so nice to see you in Stockholm when we received the Nobel Prize in December. Your Nobel lecture was especially impressive, as I learned your perspective on science firsthand. Although this time is a video message, I look forward to visiting you in Austin after the coronavirus problem settles down. I anticipate that you will continue to be healthy and active.
Hi John, happy birthday. All the best to your 98th birthday. I think we all wish you the very best for the next years, more years to come, more years in science. Thanks for really great and inspiring research and work. You influenced so many, and of course also me. And I will be happy to do further research on the really fertile grounds you created. Thanks, you.
Dear John, a quick hello from Paris, from your favorite supporter and great admirer, to wish you a happy 1980 birthday. John, over the years, you have always been my model to follow and my spiritual father. Happy birthday again.
Hi John, happy birthday. 98 and going strong still. We are very happy to see you in Stockholm last year. Good continuation and some more signs. Cheers.
Professor Li Chen-Chen and I would like to congratulate on your 98th birthday. Following your pioneering work on solid electrolyte for lithium and sodium battery, our lab also focuses on this research direction and is trying to commercialize solid-state lithium and sodium-ion batteries. All the staff and students in our lab wish you happy birthday.
Hello, John. Your legendary scientific career has encouraged the whole electrochemistry community, especially the younger generation. On behalf of the International Society of Electrochemistry, ISE, I wish you a very, very happy 98th birthday.
Greetings from Houston. Gita and I want to wish you a very happy and healthy birthday. Stay healthy, John.
Dear John, I wish you a very happy birthday on your 98th year. May God grant you good health, continued success, many smiles, and many good laughs. And congratulations on your Nobel Prize.
Morning, John. Happy birthday. This is Ken Buckmeyer, Northwestern, and we're standing in the Shakespeare Garden, dedicated to the Midsummer's Night Dream. You know probably very well. Happy birthday, John, and all the best.
Hi, Professor Goodenough. Happy birthday. And it was a great honor to see you then, and wishing you happy birthday today.
我是兰州大学的严恒华，值此 John Goodenough 教授98岁生日之际，我代表我们学校以及我们全体的学生和老师，以及分享了 John 研究成果的同道们，表示祝贺，同时也要祝贺本次大会圆满成功。
Happy 98th birthday, John. In past years, as one of your collaborators, my group and I have been honored to publish several papers with you. You are a shining pioneer for all of us. We all tend to follow your successful example as we try to solve scientific problems and to leave the world a better and cleaner place. Happy birthday to the one who goes before us and blazes a trail for our success. I wish you all the best, and I look forward to more and closer collaborations with you in the future. Happy birthday.
尊敬的John Goodenough 先生，我是北京清华大学南侧文，恭祝您98岁生日快乐，福于东海，寿比南山。
Dear Professor Goodenough, I'm Hui Chen from China. 5 years ago, I had the great honor to visit you at Austin. At this special moment of your 98th birthday, I sincerely hope you have a very good health and a long life. Happy birthday.
Dear Professor John Goodenough, I'm Jun Chen from Nankai University, currently the chairman of CSE, namely Chinese Society of Electrochemistry. On behalf of CSE, it's our great pleasure to celebrate your birthday. Happy birthday! We do thank you for your pioneering research and outstanding contribution to lithium-ion batteries. Through this Wiley online symposium, create a rechargeable world. We are sure that what you do for rechargeable batteries will make a better tomorrow.
Bonjour, Professor. Hello, John. And I thought that you might appreciate this little clin d'œil from your French boy as you used to call me 25 years ago. And I would like to thank you again for all what you did to many of us and for science in general.
Bonjour, cher John. Today we celebrate 3 things. First, today marks your 98th birthday. I wish you a good health and happiness. Second, your Nobel Prize 2019 in chemistry. It is well deserved as the culmination of many scientific breakthroughs. The third, we celebrate our 25 years of continuous and fructuous collaboration on lithium-ion and solid-state battery. Thank you for your help in my scientific careers, our friendship, and I will never forget your best words. Stay humble. I wish you bon for 100 years and plus.
Hello, John, my father in science. Happy birthday to you and congratulations on your Nobel Prize. All the solid-state chemists I know waited for the announcement for a long time. This is a picture of you, my wife, and my granddaughter Ayaka, taken 14 years ago. Maybe Ayaka joins your group in a few years. I wish you a good health. Bye.
John, it's a great honor to say happy birthday to you on behalf of the entire Battery 500 Consortium team. I would like to thank you for the exceptional contribution you have made to the scientific community and to our team. You have been a great leader, a great team member, a great mentor, and above all, a great colleague and a great friend.
And congratulations for your birthday and congratulations for your Nobel Prize last year. That was very exciting news and I'm very proud of that. Your presence is always in my mind. Please keep your health and congratulations again.
Dear Professor Goodenough, hearty congratulations on the great occasion of your 98th birthday. Thank you for your pioneering and revolutionary work, which encouraged all of us to pursue our research work. I wish you very healthy and active years ahead.
Happy birthday, John. I want to take this chance to congratulate you and your colleagues on Nobel Prize in Chemistry. You have inspired me in 2 research directions. One is lithium phosphate interface with carbon coating, and the other is solid-state batteries.
Happy birthday, Professor Goodenough. It's a great honor to work with you and also with many of your ex-group members. Enjoy the party. Thank you so much for creating our field.
Hi, John. Happy birthday. I would like to thank you for your pioneering work on lithium-ion batteries, which has helped powering the whole mobile world. I also benefit personally by looking up to you as a role model and by working with you at Battery 500 Consortium. Again, happy birthday, John.
Now star gaze up at you from afar.
Shining brightly in the night, northern star, you are my light.
Your being so for my face, I wish to remain in this beautiful place.
Silenced by your beauty, northern star, you flow through.
Northern star, you are so bright. I look up to you every night.
You help me deal with strife. Northern star, we wish you live a long life. Happy birthday!
Happy birthday!
Hi, John. This is Shirley. I hope you like the Lego that my son Jason made for you. Happy birthday. 98 is a really big, inspiring number. And thank you so much for all the support and all the inspiring things you have done for our field. And I really wish you the best health in the coming year. And we look forward to celebrating the same day next year.
Hi, John. Wish you a happy birthday. Hope to see you soon. God bless.
Birthday, Professor John. I remember pleasant days in Oxford where we worked together on lithium batteries. and all my family visited your house at Linton Road. I sent a photograph taken at that occasion.
Hello, Professor Goodenough. Here's long distance happy birthday to Professor Goodenough from Korea. Wishing you a day filled with happiness and a year filled with joy. I always admire your enthusiasm for pioneering works of developing cathode material, which is very important component for lithium ion batteries. I hope this COVID-19 passes soon, and I want to be there for your 100th birthday.
Hello, John. It is really my honor to be able to say happy birthday, happy 98th birthday. What an accomplishment. What an accomplishment your life has been. But more than anything, what I respect more than anything is your openness and your love for God. And may you have many more years of productive and successful research.
Representing the editorial teams at Wyoming for advanced energy materials and advanced function materials. It is truly a privilege to participate in this exciting event. Happy birthday, Professor Goodenough. We wish you happiness, love, good health today and always.
Thanks. Now we invite Professor Manthiram to introduce Professor Goodenough's big contribution to lithium-ion batteries. Professor Manthiram has been working with Professor Goodenough from early 1980s. He is now a professor in the University of Texas at Austin and a top scientist in the energy material and rechargeable batteries. He is the Kochler Family Regent Chair in Engineering, the Director of Texas Material Institute, and the Director of Material Science and Engineering Program. Now, welcome, Professor Manthiram.
Thank you, Yunhui. First, happy birthday to John. I'm humbled to give a brief account of Professor Nobel laureate's accomplishment over the past 70 years. John started his career in the 1950s at the Lincoln Laboratory in Massachusetts. He was always passionate about working with solid-state chemists as he was a physicist. During those days, they did seminal work on the physics and chemistry of transition metal oxides. So I would like to point out a few accomplishments. They were working on understanding the magnetic properties of materials, and his group discovered the first random access memory based on ceramic oxides for digital computers. He also worked on understanding the cooperative atomic orbital ordering in solids and Jahn-Teller distortion. We talk about a lot in the battery community, is one of those. They worked extensively in understanding the rules and the science of magnetic interactions in solids, how the electronic configuration and how the chemical bonding influence or control the magnetic ordering in solids. For example, how direct metal-metal interaction or 90 degrees metal-oxygen-metal interaction or 180 degrees metal-oxygen-metal interaction, how do they affect, influence the ordering, magnetic ordering to give antiferromagnetic, ferromagnetic, or ferrimagnetic. And out of that, we got the Goodenough-Kanamori rules for magnetic interactions. While he was at the Lincoln Lab, he also developed one of the first solid sodium ion electrolyte, the Nasicon, which the battery community is very familiar. Then in 1976, he moved from Lincoln Lab to the University of Oxford in England, and that's where the discovery of oxide cathodes happened. So there were three visiting scientists or postdocs who came from three different parts of the world to work with him. First, Kyoichi Mishishima from Japan worked with John. So John used all his expertise he developed over 30 years from the 1950s with Mishishima to develop the layered lithium cobalt oxide. Mishishima left, then Michael Thackeray, he is with us today as one of the speakers. He came from South Africa and they developed spinel LiMn204. Mike left. I came to John from India in 1985 and we worked on a series of iron polyanion materials, and that's where the inductive effect was first identified. So even today, these are the three classes of broad classes of families, layered, spinel, and polyanion oxides. They are practically viable. Then we moved to the University of Texas at Austin in 1985. The high temperature copper oxides became a very hot field as soon as we moved here. So John was very deeply engaged on copper oxide superconductors involving Professor Yang Shao-Horn, who is still here at the University of Texas at Austin. So we are very busy with the copper oxide superconductors for several years. And John was very keen on understanding or putting forward a mechanism for understanding the superconductivity. He still continues his work on the electrode and electrolyte materials for batteries, including sodium ion batteries, as well as all solid state batteries. The journey continues, but continuing the journey requires resources. So the US Department of Energy is very supportive for the past 25 years to support Professor Goodenough's research, along with some of the speakers. Today you will have their research as well. So I have a message from the program managers at the DOE. So the message is, it has been a privilege and an honor to support your scientific efforts in lithium batteries. Your research and breakthrough will have a lasting effect on the lives of people worldwide as cell phones, laptops, and electric vehicles become commonplace, and as energy storage enables a stable and affordable electric grid using renewable resources. Now, so far I talked about scientific achievements, but to me, the most important aspect with John being with him for the past 35 years is his personal qualities. First, he is the greatest scientific mind of our time. He has dedicated his life to science for 70 years. He always has a sense of purpose. He is thoughtful and curious, with full of love and respect for everyone, no matter whether you are an undergraduate student or elementary school student. He treats everybody the same way with a good heart. His trademark, interdisciplinarity. He knew about interdisciplinarity before anybody ever thought of it. I mean, 1950s, 1960s. He has been a strong force to bridge chemistry and physics and then translating that into technology. One example is lithium-ion batteries. He's a good listener, no matter who you are, always looks for learning from others, including students. Anyone can talk to him at any time about any topic. Yes, he will entertain you with that laugh. Never gets stressed out. He will always say when there are issues or problems, my boy, one step at a time. And more importantly, those of you who are young listening, he sleeps at least 8 hours a day. That's why we have 98th birthday, and I'm sure we are going to have the 100th birthday pretty soon. He has high moral standard. He many times says, always be honest about what you do and what you say, and leave the rest to the Lord. He is a role model to everyone, not only in science, but also in our daily life. He is inspirational to everybody, including me. Happy birthday to John. We wish him with good health for years to come. I really look forward to the grand 100th birthday celebration in Austin in 2022. Please mark your calendar. Thank you. Happy birthday.
Okay, so now there should be some comments from Professor Goodenough. Can you please come on?
Where are my comments?
Welcome, welcome.
Hey.
The floor is yours.
Dear friends and colleagues, I'm grateful to my Creator to be able to celebrate with you all my 98th birthday. I thank Wiley Publications, Professor Yunhui Huang, Professor Arumugam Manthiram, and editor Dr. John Ulrich for organizing this virtual symposium. My thanks to each of the speakers for their willingness to honor me with their talks. Our adventures together in material science and engineering have been the fabric of my life. I have had a privileged life. During the Great Depression, I was given a scholarship to attend Groton School for 6 years, after which I was given a scholarship to attend Yale University. During the summers, I tutored in grand homes. My father gave me $45 to buy books my freshman year at Yale, and I was able to never again accept money from my parents. I had kayaked down the Ivalo River from Finland to Norway, tutored in grand homes, married and lived with a wonderful lady for almost 66 years before I made my home in Texas. I was vacationing in Norway when Hitler moved into Poland in 1939. I was a sophomore at Yale University when the Japanese bombed Pearl Harbor. And I had spent World War II as an Army meteorologist before going to MIT. I completed my undergraduate requirements for graduation from Yale University before and while I served in the U.S. Army during World War II. I was mentored during the war by Yale math professor Egbert Miles, whose wise counsel helped me to make several critical decisions. He advised me not to join the Marines, but to become a meteorologist, a profession I practiced throughout the war. After the war, he made it possible for me to study physics at the University of Chicago. Egbert Miles was a wise, resourceful mentor and friend. Upon completion of my PhD studies in 1952, I took a job at the MIT Lincoln Laboratory. At the MIT Lincoln Laboratory, I helped to develop the ferromagnetic materials that made possible the first random access memory invented by J. Forrester. When we were called to Jay's office after we had succeeded, he said to us, "Thank you, gentlemen. Now that you've worked yourselves out of a job, what are you planning to do?" Others went to industry with their expertise. I went home and planned my next project. In 1976, I was invited to become the head of the Inorganic Chemistry Laboratory in Oxford, England. My years in England as a chemistry professor were transformative for me. While at Oxford, I investigated lithium insertion into layered oxides as cathodes for lithium-ion batteries. The lithium-ion battery that powers the wireless revolution emerged from that work. After 10 years at Oxford and a forced retirement approaching in England, I accept an appointment as a professor of engineering at the University of Texas at Austin that had no retirement age requirement. My years in Texas as a professor in the Department of Material Science and Mechanical Engineering have been a joy. During my years at Texas, we have brought together backgrounds in physics, chemistry, and engineering to develop new materials. The confluence of different backgrounds has been productive. I'm most grateful to the University of Texas for allowing me to continue to work, and to my colleagues for their help. To each of my friends and colleagues over the years, I give you my grateful thanks, and I thank all of you for your participation in my 98th birthday.
Professor Goodenough, thank you so much for being with us today and for celebrating your birthday with us. We really appreciate it. It's quite an honor for me, and I think an honor for all of us. Thank you so much for being here. And once again, happy birthday from all of us.
Thank you.
Following this, we are moving then to the first scientific talk of the day from Dr. Michael Thackeray. He graduated from the University of Cape Town, South Africa, receiving his PhD in chemistry in 1977. After spending 20 years on battery-related research for the Council of Scientific and Industrial Research, CSIR, in Pretoria, that included a 15-month postdoctoral visit in 1981 and 1982 at John Goodenough's laboratory in Oxford University, UK. And he'll talk about that today, as you can see from his title. He subsequently moved to Argonne National Laboratory in 1994 near Chicago in the US, and is currently an Argonne Emeritus Distinguished Fellow. Dr. Thackeray, the floor is yours. We look forward to your presentation.
Well, thanks, John, and good morning and good afternoon and good evening, wherever you are on this beautiful planet. But first, happy birthday, John. It's an absolute privilege to be here today with you to honor you and to celebrate your 98th birthday. I'd like to spend 15 or 20 minutes on telling you a personal story about Spinel, and in particular the impact that the sabbatical visit that I had to John's lab at Oxford University in 1981-82 had on my career over 40 years. So the story starts in South Africa at the Council for Scientific and Industrial Research in 1974. And in those days, the Middle East crisis, the Yom Kippur War had been initiated. And Johan Kutzer, who you can see on the right-hand side there of the slide, initiated battery R&D in South Africa in response to the war and the need to find alternative sources of energy to power electric vehicles. We were funded both by government to do basic research on high temperature lithium batteries, and later industry came in to support us to do some applied research, which led to the development of a sodium nickel chloride high temperature battery as an alternative to sodium sulfur. And that program was highly successful. It resulted in a development of buses and cars in conjunction with help from Anglo-American in South Africa, Beta R&D in the UK, and Daimler-Benz in Germany. But there was one major spin-off from this high temperature lithium batteries. We also were following what Argonne was doing in the United States in the development of their lithium aluminium iron sulfide battery, and we replaced the iron sulfide cathode with iron oxides because they were less corrosive. We looked at two iron oxides, Fe3O4 and alpha Fe2O3, and discovered that these materials operated by a beautiful lithium insertion ion extrusion reaction. Unfortunately, the operating voltage of these systems was too low for practical use. But the beauty of these reversible insertion and extrusion reactions was that the cubic close-packed oxygen array remained intact during the electrochemical process. But in each case, the spinel structure was regenerated on charge, particularly in the case of Fe3O4. If one started with alpha Fe2O3, which was hexagonally close-packed on charge, that didn't go back to that particular crystalline form, but rather to gamma Fe2O3 spinel. So there was something going on in the stability of spinel framework structures and rock salt. The low voltage of the systems didn't interest Anglo-American, our sponsors in South Africa at all. So I wrote to John in 1981 to ask if I could come and spend some time with him and to investigate the reactions of spinels, and in particular Fe3O4 and Mn3O4 at room temperature. When I arrived at Oxford in 1981, John called me aside and he said, well, you know, spinels are really like gems. They are line phases. Where is the space for the lithium? And spinels are indeed like gems. The most famous spinel, I think, is found on the Black Prince's on the Imperial State Crown. It's called the Black Prince's Ruby. You can see it there in red, but it actually turned out to be a spinel rather than a ruby. But we went ahead and looked at the reactions of lithium with these two spinel compounds and found that the B2O4 framework of the spinel structure remained totally intact as the spinel, as lithium was inserted into the spinel. But in order to create the space, the cations on the tetrahedral sites had to be displaced into octahedral sites. I remember Bill David and I, who had just done the work on the Fe3O4 and noticed these structural features, we took the results to John, and it wasn't 5 seconds or 10 seconds before John said, well, if that's the case, what we have to do is to replace the tetrahedral site cation with lithium. And that was the start of the lithium manganese oxide project. Peter Bruce joined the team as the electrochemist. So this is a shot of the staff of the ICL in 1982, and you can see John there in the center. But there were some other notables at the ICL at that time. One was Peter Dickens, who turned out, or was the PhD supervisor of Stan Whittingham. They'd been working on bronze structures and hydrogen insertion in the late 1960s. But out of this, since John Goodenough's time, there have been several what I call ICL lithium battery notables, John in particular, of course, Stan Whittingham, 2 Nobel laureates, Bill David and Peter Bruce, who worked on the manganese spinel, and as Ram Manthiram said earlier, he initiated some of the very early work on polyanionic structures such as iron sulfate. I can't not show this photograph. It was taken on the 9th of October last year when the Royal Society presented John with the Copley Award, and it just so happened that the Oxford Spinell team from 38 years ago was present for the dinner. Peter Bruce on the left and Bill David on the right, and me in the middle, and of course John in the front. But of course, as many of you might remember, 9th of October was the day that the Nobel Prize was announced, and so it was a double whammy for us, and we had an excellent dinner that evening, and just lovely that the Oxford Spinell team of 4 was there to celebrate with John. In 1983, I went back to South Africa, and there the CSIR team were the first to extract lithium electrochemically from the spinel at 4 volts. But it was a little bit later on, in the late 1980s, that we realized that Sony and Sanyo and National Panasonic in Japan were beginning to talk about using Li-204 as a 4 volts in rechargeable lithium batteries. So we jumped back on the bandwagon and looked at the lithium manganese oxide phase diagram in detail, and noticed some very important factors that if you increase the manganese 4 manganese 3 ratio, you could do this, but you could do this by increasing the lithium content in the spinel electrode. Although this slightly reduced the capacity of the electrode, it suppressed the Antilla distortion and enhanced cycling stability at 3 volts. It suppressed dissolution at high potentials and eventually found its way into lithium-rich commercial spinel products. A couple of years later, in 1993, John's layered lithium cobalt oxide had already taken the world by storm in being used in the first lithium-ion battery products. Layered lithium nickel oxides were also known, but there wasn't an anhydrous lithium manganese oxide. So we started trying to think of ways to produce a layered lithium manganese oxide, and we started off by looking at Li2MnO3, which is rock salt. It's electrochemically inactive, but used it as a precursor to try and make a layered lithium manganese oxide structure. It so happened that John Hunter in 1981, when we were working on spinels at Oxford, was also looking at Li-204, but in his case, he was leaching lithium and manganese oxide to make lambda MnO2 as a electrode for a primary lithium, high voltage lithium cell. But we noticed that this acid treatment leached out lithium during the chemical reaction. And if you look at the formula of Li2MnO3, it's Li2O.MnO2. So we took Li2MnO3 and used sulfuric acid to, in a similar sort of fashion, to strip out some lithium from the manganese oxide structure. Although this was accompanied by some lithium proton exchange to yield a charged product that you see on the top left. Once one reinserted the lithium under non-aqueous conditions, either chemically or electrochemically, we created a discharged cathode, which consisted of 2 components, Li2MnO3 and a layered Li-MnO2 structure. So this gave us some thoughts of using Li2MnO3 to stabilize layered materials. In 1994, I left the CSIR in South Africa and headed towards Argonne National Laboratory in the United States. And we used the work that had been done at the CSIR largely as a platform to continue studies on lithium manganese oxides. And we used this idea of Li2MnO3 to stabilize layered NMC type materials. The strategy there was to, again, embed Li2MnO3 as the inactive component and to stabilize the structurally compatible active layered NMC component. And this idea is analogous to the structure and electrochemical operation of gamma MnO2, which consists of 2 components, an inactive beta MnO2 component, which is structurally integrated with an electrochemically active RAM-slide MnO2 component. These what I call layered materials, LiTermino3.LiMO2, worked in a certain sense quite well. It was Jeff Dahn who first pointed out that if you took these materials and charged them above 4.5 or 4.6 volts, you could strip lithium and oxygen out of the structure and increase the capacity of the material considerably by as much, and to get capacities of about 250 milliamp hours per gram. Unfortunately, these materials suffer from voltage fade, which is attributed to structural instability and particularly the migration of transition metals into the lithium layers. But if you control the reactions and narrow the voltage window, you can actually get very good cycling performance from some of these materials. They only operate really well at low current rates, and there is some hysteresis on charge and discharge, which doesn't count in its favor as regarding power output. So there were these problems associated with these layered materials, and we're still working on them at Argonne. And we've looked at the problems, and we extended the concept of using these structurally integrated materials and extended that to a 3-component system where we introduced some spinel into these structures. And the motivation behind that was to use the spinel as pillars to stabilize layered structures. And we all know that in the spinel structure, 25% of the transition metals are located in the lithium layers. And the compatibility of spinel and Li4Mn5812 and Li2Mn3 can clearly be seen on the TEM image on the right-hand side, where you can see this beautiful integration between the 2 components. The reason for that is that the lattice parameters and the X-ray diffraction patterns of these 2 materials are almost identical, yielding this beautiful nanocomposite structure. So we've advanced our knowledge of these materials, and by 2015, we had scaled up some of these materials and had discovered that if one introduced between 5 and 10% spinel, which you can see in the green and the blue plots on the left-hand side, both cycling stability and on the right, rate performance of these materials is considerably improved if you have between 5 and 10% of spinel within the structure. TEM images, however, have demonstrated that it's more likely that the spinel in these cases is found at the surface rather than within the bulk. So I just want to end off with some comments as to where we are now with work on spinel-related materials. And instead of using manganese spinels as a stabilizing agent, we're looking at lithiated spinels now, because, and there's this whole family of lithiated cobalt spinels that are fairly unique because they can be synthesized in air at 400 to 500 degrees C, unlike many of the other lithiated spinels, such as the manganese systems, and of course the lithiated nickel spinel has not yet been made at all, chemically or electrochemically. But a lithiated spinel has a rock-salt structure, as does these composite Li2Mno3.LiMo2 structures. So it seems as though it might be more worthwhile and more compatible to use a lithiated spinel rather than a stoichiometric spinel, which has got lithium in the tetrahedral sites. Another advantage is that relative to manganese and nickel, cobalt has a low propensity to migrate during the redox reactions in these composite electrodes. What we have found fairly recently is that aluminium substitution in these lithiated cobalt spinels does some really wonderful things. It changes, if you look at the left-hand side, the black dots represent the lithiated spinel curve, and you can see between if you start off on the right-hand side and extract lithium, it operates in a two-phase reaction process. Up until about 70% of the lithium that's been extracted, then unfortunately we've got some layered LiCO2 material in that sample, which is a little bit difficult to remove. If you look at the aluminium substituted material in red, the aluminium substitution changes the nature of this reaction radically from two-phase behavior to what seems like an apparent single-phase process. Aluminium substitution also increases the cell voltage. And even more exciting is that the lithium cobalt aluminium oxide, a lithiated spinel like lithium titanate, LTO, a titanate spinel, both of those are zero strain electrode materials. There's virtually no change in the lattice parameter of both these compounds. So now we have a really nice model system where we can combine an LCAO cathode with an LTO anode. And what are the implications now of designing a 2-volt all solid state lithium titanate, lithium cobalt aluminate cell? I think just from the question of time, I'm not going to spend too much time on this slide, except to say that some very elegant structural work has been done at the Advanced Proton Source by E.J. Lee. And the realization now is that the aluminium substituted material contains what seems to be about 2% aluminium on the 16C sites, which then impacts the diffusion of lithium through the 8A16C, 8A16C tetrahedral octahedral site network for lithium diffusion. And this gives rise to the slight change in the electrochemical profile. So in conclusion, the spinel story is not yet quite over. It's been a long time since we started working on it, but there's still some exciting things going on. And although nickel-rich and NCA and NMC are still in vogue, spinel-stabilized lithium and manganese-rich materials still hold some promise for the future. And if I can go back to the original patent that John and I took out in the early 1980s, it seems as though we might be closer now to capitalizing on this 37-year-old concept of an all-solid-state spinel cell, because the title of our patent was solid-state cell wherein an anode, solid electrolyte, and cathode each comprise a cubic close-back framework structure of the spinel. So we'll see. We just need to get a really good spinel solid electrolyte now, and we could have a really interesting all-solid-state system. So just finally, just some comments about life and the significance of being 98. I've known John for almost one half of his lifetime. And the second half of John's life has been just as prolific, if not more prolific, as the first, capped by his enormous contributions to lithium-ion battery science and technology, and of course with the award of the 2019 Nobel Prize in Chemistry last year at the age of 97. Very few will emulate his lifetime efforts and achievements. And just finally, I'd just like to quote from William Makepeace Thackeray, who's a relative, he was an English novelist in Victorian times. And it just seems to me that William Makepeace Thackeray's and John Goodenough's philosophy on life have been the same, particularly when you take into account the fact that John was 97 when he won the Nobel Prize. And this is probably a message for the younger generation. Do not be in a hurry to succeed. For what would you have to live for afterwards? Better make the horizon your goal. It will always be ahead of you. Thanks very much.
I thank Professor Thackeray for sharing us with the great history to discover, the spinel oxide. we collect many questions from the broadcast, but because of the time is not enough, so we will transfer the question to you by email. Here, maybe we just answer one question. Because everyone know you discovered, I mean, the spinel cathode material with Professor Goodenough. So the audience, they want to know, is there any general model to discover the cathode material? And what about the future direction for the oxide cathode material?
Yeah, well,
thank you.
Yeah, well, an interesting question. You've got to dream and you've got to think big, you know, and sometimes you've got to have quiet times just to reflect. You know, the world has become so busy that one needs time, I think, to be innovative. Lithium metal oxides are reaching, I wouldn't call it saturation, but so much is known now about them relative to what was known 40 years ago. But I think that some of the developments these days, I mean, there's so much work going on around the world on all the major continents. So it's difficult to find something that's new, but every now and again, and I take this, maybe it's a small example, but one of the aluminium substitution in the cobalt, I think that we've hit on something which is really intriguing, which is giving us new life to maybe do things that might help us just improve the performance of lithium-ion batteries in the long term.
Okay. Thank you. So, John, yes, thank you. So, John, now next speaker, John, please.
Yes, thank you so much for this very interesting talk, Professor Thackeray, Dr. Thackeray. I really appreciate it. It was a very nice talk, and thank you as well for the questions from the audience. We had some connection difficulties with Peter Bruce. Professor Bruce, I believe, though, has managed to join us here just a few minutes ago, so I will go ahead and introduce him. He's a Wolfson Professor of Materials at the University of Oxford in the UK, Chief Scientist of the Faraday Institution, and a Vice President of the Royal Society. His interests embrace materials chemistry, electrochemistry, especially lithium and sodium batteries, and recent efforts have focused on lithium-rich cathodes for lithium-ion batteries, sodium-ion battery cathodes, and lithium-air battery, as well as solid-state batteries. Today, I believe he will talk about a unified model of oxygen redox and lithium-rich cathodes. Professor Bruce, if you've managed it in just in time, the floor is yours.
Well, thank you very much, John, and welcome. I'm delighted I could join you at last. It's taken most of the meeting up to now to figure out how to connect with you. So it's a great pleasure on your 98th birthday. And I'm sorry we can't all I guess this is the nature of the world. So I chose topic of lithium cathodes, really lithium-rich cathodes, because of course, John, you've had a breakthrough with lithium cobalt oxide that led largely to the battery. And also because, of course, Mike is a pioneer of these so-called lithium-rich oxygen redox materials. And so I thought it would be a fitting topic for me to talk a little bit about today. So what I want to look at is, or what we should recognize, I guess, is that there's an insatiable desire always to have more energy density, and a large measure of that, a large barrier to that is the cathode and the ability to store charge in the cathode. And as we know, conventional cathodes are limited to charge storage employing redox reactions on the transition metal. And of course, the sort of thinking behind these lithium-rich oxygen redox materials is if we could exploit the oxygen redox as well as the transition metal redox, we could increase the capacity of these sorts of materials. So I won't need to dwell, I'm sure, on the introductory parts here, so I'll go through those quite quickly. As we know, there's no such thing as a free lunch, and the possible increase in energy storage that the oxygen redox cathodes might offer us will come at a price, and that price is that we have to figure out some problems that these materials have. And the one that I'm focusing on here especially is the first cycle redox hysteresis. So what you see on the left is the representation of the crystal structure looking along the planes of a typical lithium-rich material. You see it represented up there. It's the lithium-rich NMC. So normally we just have nickel, manganese, and cobalt on the transition metal layers. Inside the square brackets here, we've got extra lithium and these lithium-rich materials, and the transition metals are represented. Sites are represented here. The lithium's in the light spheres. If we use this as a cathode and we charge it up, this is the sort of profile we get, the voltage profile on the first charge, the redox capacity. And if you charge and then discharge again, you pretty much follow this same line. But if you go further, and you can, and start oxidizing the oxide ions, that's this region here, you have a lot more capacity, but the price you pay is when you discharge again, you come back down at this lower voltage. And so you've lost 1 electron volt of energy, 1 volt between the charge and the discharge. And although, as I'll show you in a second, you can of course cycle around this region here, you would really like to cycle back and forth along this voltage profile to gain not only the extra capacity of oxygen redox, but also the relatively high voltage, which is high enough to be useful to increase the energy storage, but not so high that it gets into the problems of electrolyte oxidation to too much of an extent. And of course, in subsequent cycles that I've just alluded to, you can cycle this and you can stick around this lower voltage if you accept that. And there's of course issues of voltage fade, etc., and still a hysteresis that you see here, even on second and subsequent cycles. But the main topic for me to focus on today is this loss of voltage on the first cycle. Just in passing, I should say this is really what a hysteresis loop. We use hysteresis for this first cycle voltage loss, but it's not really a hysteresis loop because it's completely irreversible. But it's a terminology, I guess, that we're kind of stuck with. So of course, this large change in voltage between charge and discharge in the first cycle signals a change in the structure. Some significant structural rearrangement is taking place. So the probe, the technique that we found, and others too have found particularly useful in trying to understand the nature of oxygen redox, because at the heart of trying to capitalize on this high capacity for practical applications is understanding the fundamental science behind what happens when you oxidize oxide ions and what structural changes are linked to that. So to probe the nature of oxidized oxide ions, RIX, this resonant inelastic X-ray scattering technique, has been very useful. Just to remind you, applied to oxygen, you excite an electron from the core level, the oxygen 1s level, so it's K edge spectroscopy, to these empty states here, and then you look at the emission from the filled states back into the empty state there. So that's the technique. It's a resonant technique, and we're just going to look at some of these RIX spectra at key points along the charge-discharge curve for our model compound, this lithium-rich NMC, which is most of what I'll say today is seen in other comparable compounds. So this is just a nice example. So here's a so-called RIX map before we enter the oxygen redox region. And just to explain these RIX maps, you have the excitation different excitation energies along the y-axis, and for each one you have an emission spectrum that's represented as energy loss along here. So this is a sort of whole bunch of emission spectra at different excitation energies. So this gives you this RIX map at just before the plateau. Here's the situation at the end of oxidation of oxide ions. And the really interesting bit is actually in here. So I'm going to blow this up. And that's this region here. So this is the elastic peak in RIX. And these progressions here, if you compare them with the progressions for molecular oxygen, you see that they have the same spacing. This is a vibrational spectrum for this oxygen species, captured in the particles, not at the surface and not evolved from the surface. These are oxygens, molecular oxygen, trapped in the particles. You see the same signature for molecular oxygen. Just in passing, to make the point that this does not fit well with an example of a peroxide species. So this is the sort of vibrational spectrum from peroxide species, which is considerably different from what we observe. So the point here is that we're seeing molecular oxygen trapped within the particles, and when you discharge, you go back to, you lose all this because the oxygen's reduced back down to oxide ions, and you see you've nothing in that region in the spectrum here, and there was nothing in this region before we entered the plateau. So the take-home message is oxidized oxide ions produce molecular oxygen trapped in the particles. We know there's always O2 involved at the surface, but this is O2 trapped within the particles. RIX is a high vacuum technique ex situ, so you're not observing any oxygen loss in the electrochemistry. So how is it possible to accommodate molecular oxygen in a structure like this? So here we have the crystal structure again, and here we're looking down onto sort of plan view down the c-axis, and this is the famous honeycomb arrangement, remembering that cobalt, manganese and nickel, the X-ray scatterings are almost identical. So if you forget the distinctions, you see this rather nice honeycomb arrangement that we're familiar with in these lithium-rich compounds. And here's the powder diffraction pattern for this material. And here's the blown up region where we see the superstructure peaks associated with the honeycomb ordering. So if we focus on this honeycomb ordering for a moment and this arrangement here, and then look at what happens when we charge this cathode up, when we extract lithium ions and electrons. We're going to look at three pieces of evidence: the powder diffraction, which I'll come back to in a moment, lithium-6 NMR, and some STEM data, scanning transmission electron microscopy. So here we're looking along the planes in STEM, and these dumbbells are what you expect to see and what you do see when you have a honeycomb ordering. When you charge up the material, you see that you lose those dumbbells, this smearing out of the light scattering. And the light scattering is from the heavy elements. These are from the transition metal ions. Basically, this is showing us that we're disordering those transition metal ions. So when we extract lithium from the transition metal layers, the transition metal ions disorder mainly in plane. And that's what we see from the PXRD and also from the lithium-6 NMR, where you see that the center of gravity of the lithium-6 NMR signal has changed from the pristine material to the discharged material, indicating that the lithiums do not go back into the same environment. So the honeycomb structure is lost, and you mainly have in-plane disorder. So putting all this together, this is the sort of picture that emerges for oxygen redox, oxidizing oxide ions. You start from the pristine crystal structure here, the blue are the lithium ions, and we just represent all the transition metal ions now with one color for simplicity. We remove lithium ions, oxidize the transition metal ions up here. So we've lost some lithium ions. We charge, we lose most of the rest of the lithium ions at the top of charge. And now we've oxidized these oxide ions. So we've weakened the metal oxygen bond. And that means it's much easier for these manganese ions to start moving around. And it just requires one hop of each manganese to create this 4-vacancy cluster with these two oxygens, which can covalently bond to form the molecular oxygen. And of course, it's the formation of these covalent bonds which produces a significant energy sink to drive this process. I mean, it's just in passing worth noting that there are two dominantly stable forms of oxygen in nature. Oxide ions, and they're ubiquitous in many, many minerals, and molecular oxygen. And it's not perhaps surprising that when you oxidize oxide ions, molecular oxygen is where oxygen wants to go. And then when you discharge again, you reduce these molecular oxygens back to oxide ions. Crucially, the lithium ions, when they go back into the structure, into the transition metal layers, they do so in different positions, as you saw from the NMR and the pristine. Now they're in these clusters. There's a difference in these crystal structures, and that's reflected in the difference of the voltage of the energy of the beginning of this and the end of discharge. So just to briefly give you a sense of the energetics here, here's some DFT calculations where the grey crosses represent different arrangements of these vacancies created by the loss of lithium from the transition metal layers. The red one is the ground state, it's the pristine material. And what you notice is when you create a vacancy cluster, and this is the simplest one, that allows molecular oxygen, you have a big reduction in the energy. And if you go from this tri-cluster to this 4-cluster, it goes down yet again. So that sort of gives you a sense of the energetics that drives this process. To get a feel for the main factor that's controlling the difference in voltage on charge and discharge, we can look at this somewhat simplified picture. So here's our oxygen sitting between a lithium layer and a transition metal layer with 1 lithium and 2 manganese, just representing the transition metal ions. I know there's a mixture of nickel and cobalt here, but for simplicity. And if we pick out the oxygen 2p state here, that's interacting ionically with lithium, very weak covalent interactions, then these oxygen 2p states will sit at the top of the oxygen valence band. Now, when you charge and discharge, the lithium ions go back into different positions. Now you have oxygens completely surrounded by lithium. And as you'll see from the DFT, we can see from the DFT, this pushes the oxygen 2p states up further. And this is part of what is involved is in single view of what happens when you oxidize oxide ions in these cathode materials, representing when you oxidize, you lose oxygen from you find transition metal ions diffuse into the empty lithium sites, and you get this so-called densification. And as you do that, of course, you become less oxygen rich. And once you get close to stoichiometric composition, this self-limits. You don't keep going. Whereas in the bulk, when that happens, you're forced, if you create more oxygen, to trap that oxygen in the bulk. So oxygen can explain the evolution at the surface, and oxygen is trapped in the bulk. And my time is almost up, so I just want to, a couple of more slides building on what you've just seen, and this comes to the work that actually is going into the special issue, which I'm delighted to be part of to celebrate John's 98th birthday. And that is that with this unified picture, what controls the balance between oxygen loss from the surface and oxygen, molecular oxygen in the bulk? Well, recognizing that all of these compounds start from the parent Li2NO3, what you see plotted here is the fraction of the capacity due to evolved oxygen from the surface. First of all, here for Li2MnO3, and then if we come down this dotted line, we come to the stoichiometric LiTMO2 composition. So this is going from right to left. This is increasing lithium richness on the transition metal sites, Li2MnO3 being one end member, where 100% of the capacity is oxygen loss, the stoichiometric compounds where it's 0. And that would be the dotted line if you simply looked at a statistical average between these two. These lines represent what happens when you dope Li2NO3 with cobalt, nickel, and with nickel and cobalt. And if we focus on the blue one, which is the nickel, you see much reduced oxygen loss in these materials compared with the average. So nickel doping has a very disproportionately favorable ability to suppress oxygen loss. And so to cut to the final message, the reason for that is that in the as prepared material, you have a close to stoichiometric nickel-rich surface layer. represented here. If you look at the analysis of the surface versus bulk composition, you see the surface 0.32 nickel, the bulk is 0.2, and you're getting close to stoichiometric quantities of lithium in the material. So the fact that the as-prepared material has a nickel-rich surface, more closer to the stoichiometric composition, sort of self-limits oxygen loss and forces the molecular oxygen to be trapped in the surface. Of course, we know we can coat particles, so there's nothing revolutionary in the idea that surface treatments will do this, but it's the interesting fact that this material sort of has a self-coated effect or self-coating effect. So I think I should end at this point. I want to thank, of course, the people who have done all the work and the funding agencies. Just to say again, it's a great pleasure to take part in this event. Thank you, John, for friendship and support and opportunities in the early part of my career, and to thank everyone else for their attention.
So thank Professor Bruce for your exciting talk. We have collected many questions, so maybe we just ask one or two questions. And the first one is, I mean, the molecular oxygen is formed, I mean, on the surface or in the bark?
It's formed in both the surface and the bulk. So oxidized oxide ions basically go to oxygen, and when they do that on the surface, of course, it's possible for them just to evolve very easily into the electrolyte. But as I mentioned, as that happens, transition metal ions migrate from the surface into the vacancies created near the surface from the removal of lithium ions, which of course accompany the oxidation of oxide. And that then densifies the near surface region, producing a core shell structure, which limits further oxygen loss. From then on, the system has to accommodate that molecular oxygen in a different way, and it does so by this disordering of the transition metal ions to create these cavities, if you like, inside the particles that will trap the molecular oxygen. And I should say this is a reversible process. You can, as I showed you in the RIC spectra, you can re-reduce that oxygen back to oxide ions again. And in fact, you can do that on subsequent cycles. So you have oxygen basically everywhere, is I suppose the summary.
Okay, thank you. So the other question is, near the end of the distillation, did you use other technology, I mean, to show the oxygen formation? Yes,
I mean, it turns out, and I should say that, of course, there are many other people working in this area that have done made fantastic contributions, and I'm just giving you our perspective on this. It turns out, you know, have been quite a challenging problem to unravel the mysteries of oxygen redox. I think many people have found this quite a difficult, challenging problem. We have used the problem with techniques such as XPS is that they tend to be very surface dominated. The benefit of RICs is that it can penetrate about 100 nanometers into a particle, so you can really sample well into the particle. But we have used other techniques, in particular oxygen 17 NMR, which is not an easy technique, but with that, again, it's a bulk average technique, so that's powerful, so you're not surface biased in the analysis. You can also quantify the amount of oxygen, and the amount of oxygen we quantify from the 017 NMR is in good agreement with the capacity, the so-called reversible capacity from the oxygen redox region.
Okay, thank you. Thanks again, I mean, for your exciting talk and your sharing. Thank you.
Thank you very much.
Thank you. Now the next speaker.
Perfect. Thank you so much for being present here, Peter Bruce, especially on the last minute. I know you had some connection difficulties and managed it just in time. So really appreciate that it worked out.
No, thank you.
The next speaker is Professor Joachim Maier. He's director of the Physical Chemistry Department since 1991 of the Max Planck Institute for Solid State Research in Stuttgart, Germany, as well as being honorary professor at the University of Stuttgart. He's co-authored more than 900 papers on chemical and electrochemical phenomena, and his major interests are solid-state ionics, electrochemistry, and interfaces. He also laid the conceptual foundation for the field of nanoionics. Professor Maier, when you are ready, the floor is yours. I believe you'll be talking about today interfacial effects in lithium and sodium batteries.
So yes, I hope you can see my talk. Can you? Hello?
Yes, I see your talk. Go ahead.
Good. Yeah, so congratulations, John, from Stuttgart again. You may remember the celebration of your 90th birthday a short while ago, where I ended my talk by reciting a few lines from Bob Dylan's Forever Young, and mentioned that I heard this song first sung by Pete Seeger, who was elected in the Hall of Fame in his 90s. So meanwhile, actually a lot happened. You received the Nobel Prize, and Bob Dylan received the Nobel Prize too, in, I would guess, slightly different fields. So at that birthday event, I gave a lecture, you see it in the background, on thermodynamics of electrochemical lithium storage, a dedicated paper to you in Angewandte Chemie. Now this time, my talk is centered around interfacial effects in these kind of systems, dealing with various modes of storage. And you see on the picture on the right-hand side shows my co-author, Robert Yusiskid. So let's start with the first storage mode I would like to consider, namely the solid solution mode. That is A here, B will be phase transformation, and Z conversion, and D interfacial storage. So solid solution is what we all know, intercalation or insertion, and the penetration of maybe lithium or sodium or whatever into the sample is a chemical diffusion process. And in spite of the importance of all this, you don't find many papers dealing, at least on an appropriate level, with these kind of questions. So one paper that you might find is something here from Werner Sitter's group, dealing with coulometric titration, so more or less high temperature chemistry. But it's the same thing eventually. You have a mixed conductor here, which is your electrode. You have the contact to the current collector, providing the electrons. And here you have the electrolyte, providing the current collector for the ions. And here you have the counter electrode. Now, if this is a 1D configuration, and if your mixed conductor shows, for example, a pure electronic conductivity, then it's pretty straightforward to understand that because electrons are fast, the metal is virtually discharged here and then travels by pure diffusion to the right-hand side. The opposite case, that your mixed conductor is predominantly an ionic conductor, then it's just the opposite. It will travel from the right to the left. Now, if, for example, your mixed conductor is 50-50 electron and ion, you may already ask the question, what is then going to happen? It's not so that your metal is virtually discharged in the middle and it penetrates to the left and the right. Rather, it comes from both sides symmetrically here, one-to-one. So in our cases, of course, one has to model a higher dimensional situation. And Rob Yusiskid did this kind of modeling. So this may be a single crystal, but it can also be an agglomerate of particles. The ionic contact is here on these sides, and the electronic contact comes from the small sides. And again, now, when your material is essentially a good electron conductor, then it starts more or less from the ionic sides. And then you would see such a shape is, you may say, unnecessarily short, because it could be equally longer for the same waiting time to be met. If your material is an ion conductor and then the electron motion is determining, then it comes from both sides, and you may directly see this shape is giving an unnecessarily long sample, or it's too long for the waiting time. For such a shape, it turns out that the transference number for the ion is perfect for 6%. So now one can turn around the question. One can say, we know the transport parameters in a given electrode. What will be the optimum shape? This is not an academic question because, as I said, this can be an agglomerate of particles. It gives you directly advice where the electronic and the ionic current collector should sit. And this may be an agglomeration of particles. And this situation here refers to a situation where we have essentially a good electron conductor. Then you can be pretty relaxed with your electronic contact. So what we call here the wiring length, namely the distance to the electronic contact, can be pretty large. Unlike the contact, the ionic wiring length, the contact with the electrolyte, with the ionic current collector. And in spite of the complication of the problem, you see in many cases at least, such a simple formula for the wiring length is obtained. If we have an opposite situation, that the material is essentially a good ion conductor, then it is so that the ionic wiring length could be large. This is directly the recipe for an old solid state battery because you want to avoid electrode-electrolyte contacts as much as possible. So you should strive for an ionically conducting electrode. Example number 2 now refers to phase change. And this is one of your favorites. We all know this. It's iron phosphate, lithium iron phosphate. There's a big miscibility gap in between. So you deal with a two-phase situation with iron phosphate with a little lithium and lithium iron phosphate with a little lithium deficiency. And if you have a multi-particle system, it can be realized by various situations that you end up with maybe such a state of charge, lithium 0.66, just as an example. So the simple situation would be having a monomodal distribution, meaning that every grain reflects these two-phase situation like here. But you also can have a situation that 2/3 of all the grains show lithium iron phosphate composition and 1/3 shows iron phosphate. Thermodynamically, the difference is that this has an additional interfacial energy. And then when you go to a nanoparticle system, in fact, this turns out to be the most likely situation. And I have to say that many groups here, you see some names, have been dealing with these kind of questions. Also with the situation that when you go to a very nanocrystalline situation, that then because of capillarity, you may even lose your miscibility gap, and this may be then even a stable composition. What is certainly not, I have at least not found in literature, is when you go to extremely small particles, and then also the particle entropy must have an influence. Let me just dwell on this, even though it may be a little academic. When you have an ideal gas and you have two energy states, it is not so that only the low energy level will be occupied because of Boltzmann, also higher lying levels. But when you have a big macroscopic system like a single crystal, you can only populate the lowest level. But if you go to a nanoscopic arrangement, a situation where you have many nanoparticulate particles, grains, then you might see fluctuations in composition, in equilibrium, around that 0.66 composition, even if the particle size is the same. Now, the whole situation is even more complicated because of ordering. And this is very nice work in collaboration with a Japanese group here, Professor Ikuhara, and our Chinese friends, Lin Gu, Zhangbao Zhu, Hong Li, Yan Yu, Shilin Li. This is aberration-controlled TM, and this shows that in lithium, maybe here 0.5 iron phosphate to take a different composition, you see staging. So it's not so that the lithium ions are randomly distributed. In lithium iron phosphate, any of these rows are occupied with lithium, that are completely empty in the iron phosphate. But here, every second row is found to be filled. So it's a kind of a staging phenomena, which makes some dips in the Gibbs free energy curve. I find it more exciting even that this is the favorable solution for a grain-to-grain contact of these two phases, iron phosphate and lithium iron phosphate, because it provides a kind of a zipping contact connecting these two grains. And we gave thermodynamic arguments in this paper that there may even be an equilibrium thickness for such a zipping phase in the middle of it. Example number 3 refers to decomposition, so what is normally called a conversion reaction. We know that when you have a material, maybe here molybdenum sulfide, that this provides a very high capacity, because 4 lithium per molybdenum here can be stored. But the disadvantage is you form a mess of phases, 3 phases. And this is hard to get reversed. So we provided one solution, one recipe for doing it. That is this kind of situation with molybdenum sulfide. It is what we call reaction confinement in storing and bringing lithium or sodium into a nanodot ensemble. So what you see here are very, very tiny nanodots of molybdenum sulfide, 0.3 times 3 times 3 nanometers. It's extremely small. And you may imagine that when you then decompose this nano crystal, quotation mark, that then you are almost like an intercalation. It's almost like a homogeneous reaction, because the phases that you form, they cannot move away because of mobility, and this is very easy to reverse. And in fact, the cycling behavior is almost a cycling behavior that you would find in an intercalation situation. Moreover, the thermodynamics is interesting because of capillarity, of the smallness of these particles, the surface energy. You reduce your EMF here by half a volt. This you can calculate, and you also find it experimentally. This is good here because molybdenum sulfide may be acting as an anode. And number D, our favorite subject in Stuttgart, here interfacial storage. And such situation is well seen, or at least in terms of the capacity, when you have your conversion reaction, you form a nanocomposite. Then you see some extra storage which can be attributed to these kind of phenomena. This is another figure out of the paper that we have in advanced energy materials, and it shows that all these interfaces that you see in a battery, they all, of course, have to exhibit space charge effects. The question is, how big are they? Now, these space charge effects may lead to an increased resistance inside, which may be detrimental, but it also can have a storage effect. Namely, whenever you have a kind of a contact between something involving the ions and some other phase involving the electrons, then you have an excess storage. We did a lot here in terms of thermodynamics and kinetics, so I don't want to go into detail. I just want to maybe mention these two graphs. This one is a situation of bulk, including space charge zones in an electrode material in contact to a current collector. But this may also be a second phase in a multi-phase arrangement where you have this excess storage. So one thing is important here, that this kind of considerations allow for a generalized picture. Bulk storage plus space charge storage. So the whole space coordinate is involved then. And what you see here, that boundary effects and bulk effects and the ratio between both of them is a function of the state of charge. You compare these two curves. Practically speaking, this is something which we are still working on, when you look for what we call an artificial electrode, that you have the two phases that are active in this job sharing mechanisms are very, very narrowly spaced, so that you may have an overlap of space charges. Then you can show that this will lead to an increased energy density, but without compromising the power density. Unfortunately, we have only demonstrated this in our model compound with silver, rubidium silver iodide and graphite. We see a beautiful discharge curve in this system. We see vacancies formed and interstitials formed, so storage deficiency and excess, but both realized in this job sharing mode. And you may imagine, and this can be also shown theoretically and practically, that when you look at this kind of motion of silver into the material, silver plus here an electron there, that this gives rise to extremely high diffusion coefficient, irrespective of the supercapacitive charging on the left and the right. So this is the highest diffusion coefficient that has ever been seen in a solid at room temperature. It's even higher than sodium chloride in liquid water. So this picture also acts as a generalization between supercapacitor and electrode storage. So my time is up. Let me just conclude by saying there are also always interfaces in batteries. Some of them you need for the functionality. Mostly interfaces have a detrimental effect because of the resistance, so one should not have too many of them. But sometimes they also may have a beneficial effect, and I was already referring to the artificial electrodes. But there are also, if you want, artificial electrolytes. We call them here, this example, Zocchi sand electrolytes, namely a synergistic liquid-solid electrolyte in which the solids are able to trap the anions, and so improving the transference number and the overall conductivity. But I have to confess, we don't have convincing materials systems for these situations, but there is a lot to be done and a lot, very large field to be explored. So I think my time is up, and let me end by again conveying my best wishes to John, and I hope that in the future we can meet in person and that I can hear your very, very beautiful laugh in person. Thanks a lot.
Okay. Thank Professor Maier for your exciting talk. We also, collect many questions from the audience. The number one, someone want to know what is the basic, the basic solid conduction, ion conduction mechanism in solid state electrolytes.
Say it again, the major mechanism in solid electrolytes?
Yeah, what is the basic solid ion conduction mechanism in solid state electrolytes?
I'm not sure if I get the question correctly. So in a solid electrolyte, as we all know, we have very fast motion of carriers and also very high concentration of carriers. So when you have then interfaces, for example, at grain boundaries, they may typically be detrimental in terms of motion. But very often the concentration of the carriers is so high in electrolytes that we don't have really practical problems. I'm not sure if the question also referred to this job sharing. So when you do a composite of a solid electrolyte with an electron conductor very intimately, and you do this very, very small, these phases, you have a perfect, what I would say, a perfect artificial electrode, because this is very fast and it can provide storage, not so that the ions and the electrons go into the solid electrolyte. This is not possible, but the ions go to the solid electrolyte and the electrons to the counterphase.
Okay, the second one, yeah, the second one, someone wants to know how to find, good mixed conductors as electrodes, like lithium cobalt oxide.
You have to ask John how he found lithium cobalt oxide. I think it is important for electrode material that it can store lithium. So the ionic point is very important, but also, of course, you have to accommodate the electrons. It is typically good when you have a transition metal oxide. Again, when you look at these kind of job sharing situations, you can have a storage without transition metals because you decouple the role of ions and electrons. So I'm pretty much excited, but I'm not sure if this is gonna end up in something practically useful.
Okay, thank you. So the third one, what is your opinion about the interfacial effect of the polymer coating?
Polymer coating?
Yeah, polymer coating.
Coating for a passivation layer, or what is meant? It's not really clear to me what a polymer coating here means. There is not too much work done on mixed conduction polymers. We did recently something on it together with Sabine Ludwig here. So that is an exciting field anyway, mixed conductivity in polymers. But it's a big field a big bottle to open here.
Okay. The fourth one. How do you think about the multivalent ion battery, like magnesium or zinc ion batteries?
So we also think a lot about alternatives, and I'm a big fan of sodium because there are many systems now already where sodium is not so bad, and even the kinetics can be very great in sodium batteries. And the electrolytes can show very high conductivity for sodium. So sodium is not at all bad. Also, the voltage that you get is not necessarily smaller than lithium. But when it comes to higher valent situations like magnesium and aluminum oxide, all these kinetic parameters, they have somewhere in the exponent a charge. And everything becomes very sluggish. So is it a charge transfer, or is it a motion inside? So I'm not too optimistic in terms of 2 or even 3+ valent cations here.
Okay, thanks again. Okay, thanks again for your talk. So now the next speak.
Wonderful. Thank you very much for that. Thank you, Professor Maier. That was a very interesting talk, and appreciate that you were able to answer some of those questions as well. The next talk is from Professor Linda Nazar, who is at the University of Waterloo, Ontario, Canada, where she's chemistry professor, senior Canada Research Chair in Solid State Energy Materials, and distinguished research professor. Professor Nazar is known for her research in electrochemical energy storage, with topics that span lithium-ion batteries, beyond lithium-ion and solid-state ionics. And the floor is yours, Linda. Please go ahead.
Well, thank you, John, and thank you everyone for attending. Can you all hear me well? It says I have a poor call quality. Not anyway, I'll just proceed ahead. So I want to thank Wiley and Yunhui Huang, of course, John, for organizing this great event, and especially for John for having a birthday, and also acknowledge the 10th anniversary of Advanced Energy Materials. So my talk has changed a little from the original title. I'm going to be talking about all solid state batteries, and hang on a second. So I'm going to be talking about all solid state lithium sulfur batteries most specifically, and advanced functional materials. And Wiley suggested I do this in light of a paper that we just had accepted in the journal, whose title is shown here. So this is what's sort of the inspiration for my talk today. You can find the paper online, I think, very soon. And so I especially want to mark this occasion by wishing John a very happy birthday. I'm one of your biggest admirers, John, and I have been for decades, literally decades. And so a very happy 98th birthday, and I wish you great health, lots of laughs in the years to come. And I look forward to attending your 100th birthday celebration in a couple of years. So there's a lot of, I think, interest in solid state batteries in general, perhaps not so much, sorry, I'm switching slides here, not so much in lithium sulfur batteries, although they have been a matter of interest. And most of these batteries consist of effectively sulfur, a solid state electrolyte of some sort, and carbon. And this is typically something like Li3PS4. And what's pretty surprising is that in the solid state, you can actually trigger the conversion from sulfur to Li2S, which is reversible. And of course, the advantage is that this prevents the dissolution and shuttling of lithium polysulfides, which are really problematic in liquid lithium sulfur cells. So this, I seem to be in a timing here, sorry. So there's other problems with these systems, with solid state batteries such as lithium limited ion diffusion, interfacial resistance at all of these interfaces, growth of lithium dendrites because they need a lithium metal anode, but I'm not going to have time to talk about those today. I'm going to be talking more about cathode challenges. And those include low active material content, often reports less than 25 weight % of sulfur, 20 to 25, and of course, the real problem of co-oxidation of the solid state electrolyte during cycling. And this is because the carbon is intimately interwoven with the solid state electrolyte, and that wires the solid state electrolyte thiophosphate, which are typically used in these cells, and thus causes oxidation. And that in turn results in very low initial coulombic efficiency of often in the order of 80%. And the low active material content results in low areal capacity. And a lot of these concepts have been reviewed, these challenges have been reviewed by Sun in a recent article in Chemical Society Reviews. So moving beyond carbon, there has been little work. I think some excellent work has been done by Stefano Passerini and Yunhui Huang, which was published in Advanced Energy Materials a couple of years ago, where they use metal dichalcogenides as a host material, and specifically a combination of carbon FeS2. And the carbon is partly needed here because of the rather low conductivity of the iron disulfide. And their data is shown here. This is on the first cycle in black, and you can see there's quite a lot of irreversible capacity, so there's low coulombic efficiency, but then this mediates after about the 5th cycle. And they achieve fairly stable capacity cycling over 20 cycles. So their composites were prepared with a combination of carbon and iron disulfide and sulfur in a 4:3:3 ratio. So they have a low sulfur content. And they used a solid electrolyte, which is effectively a amorphous Li3PS4 combined with lithium iodide. The material itself is completely glassy. And as I said, they achieved a capacity of about 1200 milliamp hours per gram, but a fairly intermediate to low loading of about 1 milligram per square centimeter. And of course, there's also a contribution from the FeS2, and they were able to achieve around 3.55 milliamp hours per gram for these material loadings. So we decided to try a different tactic, which is to use a metallic disulfide. And our material of choice was vanadium disulfide. So it has comparable electronic conductivity to graphene on the order of 3,000 Siemens per centimeter. So it's really it's truly metallic. It also exhibits fast ion diffusion with a low migration energy barrier of about 0.22 volts. This is reported in these papers cited down below. And particularly interesting is that it's redox active within this lithium sulfur window, so therefore it provides extra capacity. And one can prepare these materials as these nanoflakes, as shown here with appropriate diffraction patterns on the right. Sorry, I'm having a bit of trouble with it. There we are. Advancing slides. So these, we call these nanoflowers, have basal dimensions in the order of 10 microns that are very, very thin layers of VS2. And these can be easily mixed with sulfur just by a traditional melt technique at 160, 12 hours to produce these composites. So critical here is that we form a sulfur VS2 core shell structure. So in other words, the metallic VS2 is completely coated by the sulfur, and the lithium thiophosphate, the Li3PS4, then incorporates on the outside of the sulfur. So it's not in direct contact with the VS2 metallic sheaths that perform the wiring for the system. So of course there have to be little gaps in between. This isn't exactly a perfect diagram, but this is the concept of this core shell structure minimizes contact between the metallic VS2 and the Li3PS4, thus mitigating the oxidation of the solid state electrolyte thiophosphate. And this just shows the good homogeneity of the system that we achieved. And this is sort of the concept here, where we have these highways of VS2 providing electrons to the system, but also providing lithium ions to the matrix of the sulfur, which is shown here in yellow. And the matrix of the solid state electrolyte then serves as a conduit for the lithium ions in this complex structure. And then we use lithium thiophosphate as our solid electrolyte, at least in these initial studies. So the first thing that we noticed was that the CV shows only two redox peaks, cathodic and anodic redox peaks, suggesting that the redox potentials that we're seeing in the system are at least overlapped. So we don't see separate potentials for the sulfur to Li2S redox compared to the intercalation of lithium and VS2. And so we have very smooth features in the solid state battery itself. You can see really just a smooth discharge and charge profile for this combination. So at the top of charge, all of the X-ray diffraction data shown here on the right suggests that we have a combination of sulfur and VS2, whereas on discharge, on full discharge, we have a combination of LiS2 from the reduction of the sulfur and LiVS2 from exchange of the lithium into incorporation of the lithium into the VS2 layer. And so these diffraction point patterns taken at point A, B, and C, D and E, all correspond to these points in the profile on the left. So point A is just the starting material where you can see the VS2. The sulfur is a little hard to see here because it's pretty much ball milled. And point B is partway through discharge, and you can start to see these VS2 shift, these VS2 peaks shift until finally at point C at full discharge, clearly they are indicative of LiVS2. And we concomitantly form the Li2S, which is indicated by the yellow triangle. So the reaction mechanism is then shown here on the right. And on charge, we simply repeat the process. The Li2S reacts with LiVS2 to form sulfur and VS2. So at the top of charge, we end up with the starting materials of the VS2, which is shown in the asterisks. The Li3PS4 peaks that you see here are simply because we had trouble actually peeling off the cathode layer from the separator in this particular diffraction pattern. And so this is just a residual separator that's showing up in the diffraction pattern. It's not from the reaction. So the take-home message here is that we have simultaneous conversion and deintercalation of sulfur and VS2 in this system. And so this is shown schematically here. In other words, in summary, the Li3VS2 provides lithium ions for the redox reaction. The VS2 provides the electronic pathway. And the LiXVS2 that forms midway is a mixed ionic electronic conductor. I think this is really very well known for most of you in the audience. And so this provides yet an additional ion pathway for sulfur reduction. So the overall reaction can be described as the following. So the proof is always in the pudding. And in this case, the pudding is the battery data. So we have here the discharge and charge profiles for the solid state battery. You can see that even on the first charge, we have excellent sulfur utilization. So we have a Coulombic efficiency of 96%. And of course, this isn't, we're not at lithium ion type qualities here, but this is for a solid state lithium sulfur cell, very, very good compared to the usual values of about 80%. And the sulfur utilization that we see in the cell is 85% as calculated from the amount of capacity that we see in this cell. And the system is pretty stable on cycling. You can see that we initially have an increase in capacity, which we sometimes call creep, and then it is reasonably stable over 50 cycles. And this is just showing the Coulombic efficiency here on the right axis. And we've also investigated the rate performance of the system where we switched from C over to 5 to C over 10. So this is the C over 5 data, the C over 10 data. We have the current density and we've cycled the cell for about 200 cycles over this period of time. It still exhibits very good cycling performance. And this is the total loading in the system. And this is actually cycled with a metallic lithium anode. So the previous data that I showed you was against the lithium indium alloy, but this proves that this indicates that the Li3PS4 is relatively stable against the lithium metal anode. It forms a passivation layer effectively at that interface of Li2S and Li3P, which then further stabilizes the system. So we're also able to create or fabricate fairly high loading cells that are shown here. So we have, this is the data for 7.7 milligrams per square centimeter and all the way up to 15.5. And of course, this starts when we really increase loading of the cell. This is of the sulfur in the VS2. Ultimately, we start to run into problems with insulating sulfur, effectively impacting that capacity. So this is a bit of a challenge. I think that we still really haven't optimized the architecture of the cell, but you know, this is our initial steps. We have reasonably good cycling efficiency, reasonably good coulombic efficiency and reasonably good cycling performance, at least in these initial stages. This is just literally our data. So we're still fighting with, of course, the issue of trying to increase current density in the systems while mitigating lithium dendrite formation. Another issue is that we have not really tackled the problem of expansion contraction as we undergo the Li2S to sulfur conversion reaction. It's a very large change in volume. And we were in the process of looking at adding binders to the cathode material before we went into shutdown. So we're revisiting that now. And of course, there's also then the concept of lengthening of when you build thick electrodes, you have a lengthened ionic electronic pathway. So we need more conductive solid electrolytes. And I'll just finish off the talk on a couple of these to address a couple of these points. So we've been investigating agueridites recently, and lithium, shows the agueridite structure, showing these Frank-Caspar polyhedra within this cubic structure comprised of the PS4 tetrahedra. So these Frank-Caspar polyhedra cages contain these lithium clusters, and within these lithium clusters, there are different types of transport mechanisms for lithium ions. So there is what is called a doublet jump between the so-called 48H positions and the 24G, which lies in the intermediate space between the doublet. And there's also the intra-cage jump and the inter-cage jump. And the inter-cage jump is thought to dominate the long-range transport. So these materials have been studied extensively. A lot of these studies are shown here. And the best thing about agueridites is that they also appear to form a fairly good interface with lithium metal, as shown by Jürgen Janik, with these being the items that form the passivating interface. So the point here is that, that there are two different positions for the anion, which is either sulfide or the halide, for example, chlorine or bromine. And these are the 4C positions and the 4A positions. So for the chlorine and the bromine agueridites, these are completely disordered. The sulfur and the halide are completely disordered over both of these sites. Whereas in the case of the iodine, it is completely ordered. And this results in very low conductivity. So this is just shows moving from chlorine to iodine, the extent of this disorder. So it's very high for chlorine, it's intermediate for bromine, and for iodine, it's literally 0. So there's no site disorder. And that correlates, as I said, with very low conductivity in the order of 10 to the minus 6 Siemens per centimeter. So it's extremely low. And now it turns out that halide-rich compositions have higher diffusivity. This is reported in a paper in JACS. We've been looking at halide-rich compositions reported here in this paper of Angavanti, and we're able to get ultra-high lithium-ion diffusivity, 10 orders of magnitude that of the lithium germanium phosphosulfide, but I won't have time to talk about that. And I'll just mention our work on the agueridite iodides, where we effectively, by introducing antimony into the lattice, substituting, so these are antimony, silicon substituted antimony agueridites. So we've taken the conductivity from very low values, shown here, all the way up to 10 millisiemens, and in fact above. And you can see that in this plot that as the conductivity increases, the activation energy drops as expected. And this increases with silicon substitution, and the silicon substitution for the antimony also increases the lithium content. And this is the main point. So we can see that anion disorder does not play any role whatsoever. It really is the lithium content that is affecting things. We're getting conductivities upwards of easily 20 millisiemens per centimeter, either for annealed, 15 to 20 for annealed versus sintered pellets. So these are super ionic conductors. And the reason for that is, the reason for that is shown in this overhead, where effectively in the pure antimony and diodide, we have 2 lithium sites whereas in the silicon substituted material, we have 4 sites. And we introduced 2 additional sites in the 48H and the so-called 4D site. And again, very little anion disorder. So one of these sites actually sits in the intercage transport pathway, and it provides a metastable site for ion diffusion. And this is what results in the high conductivity. So anion disorder in the iodide is irrelevant. It really is this new pathway for transport in the intercage regime that we are able to develop by literally stuffing lithium into the structure by virtue of incorporating silicon. So we go from a lithium poor regime to a lithium rich regime. And so Yifei Mo has shown that when you stuff lithium into a structure, you effectively populate these high energy sites, and that activates concerted ion migration, lowers the activation energy for diffusion. And we believe that this is the mechanism that's responsible for our conductivities of upwards of 15 to 20 millisiemens per centimeter. So I'll just end off. Well, I was going to end off with a slide of Spinel, but that's missing from my overhead. So instead, I'll just, my time is almost up. So I'll end up reminding, or just reminding everyone of the sponsors for our work. This is mostly done partly by NSERC. BSF sponsored our antimonide aguridite work. And I want to say once again, happy birthday, 98th birthday, John. You've been a true inspiration to me for so long. It's in many different areas, and so solid state batteries are just one of them. And so I'd like to thank all of the people that contributed to the work, and thank you for your attention.
Okay, thank Professor Nazar for your interesting talk. I mean, in solid state lithium sulfur batteries. We have collected several questions. The first question is, what is the expected energy density in solid state lithium sulfur battery as compared with the traditional liquid lithium sulfur batteries?
Yeah. Well, you know, I think it's a little too early to start judging on energy density, simply because it really depends on the type of electrolytes that you bring into the system and how much sulfur you can really incorporate. So what we really need to do in order to increase the energy density of the system is to move above where we are now, which is about 35% sulfur. But we're also using the vanadium the VS2 as a capacity increase. So we would like to incorporate more sulfur into the system, upwards of about 60%, and then I think we can start talking about practical energy density. And that's going to require the use of the binders and more complex architectures. So I would like to hold off on predictions of energy density at this point until we sort of move to the next step.
Okay, thank you. So the second one is, what is the future, I mean, for lithium sulfur battery? Is a solid state lithium sulfur battery or the traditional, I mean, the liquid sulfur batteries?
Well, always the difficult questions. I personally think that the future is probably in solid state, or what I would call quasi-solid state. The jury is still out. I think we've been all fighting with the problem of dissolution reprecipitation in cells, trying to really, I mean, there's been so many different approaches to this that have, to a large extent worked, but a large extent still have a long way to go, that I think it's time to turn our attention to different ideas. And so this is, again, you've asked, it's sort of an opinion here as opposed to an absolute proclamation, but I think that quasi-solid state is probably going to have a lot of advantages in controlling that dissolution precipitation. And it's pretty clear that we can undergo the solid state conversion fairly readily. So it's a matter of finding the right, as I said, architecture and so-called ingredients to really facilitate that conversion. And I think that will probably overcome, I think that will supersede the traditional liquids itself.
Okay, thank you. Yeah, because there are many questions. Maybe I will transfer to you by email. Thank you again for your talk.
Thank you.
Thank you. So now the last speaker.
Great. Thank you so much, Professor Nazar, for a very interesting talk, and Professor Huang for moderating those questions. The last scientific talk of today is from Professor Yang Shao-Horn, who's the W.M. Keck Professor of Energy at the Massachusetts Institute of Technology. Her work centers on using chemical physics to understand and control molecular reaction details for the dynamics at electrified interface and transport properties for sustainable energy and chemicals. She also serves on the MIT EI Energy Council and is co-director for the MIT Low Carbon Energy Storage Center. Professor Shao-Horn, the floor is yours. I really look forward to your talk.
Thank you. Good morning, good afternoon, good evening. I'm delighted to be here celebrating John's 98th birthday. I want to thank the organizers for the symposium. John, happy birthday. John is extremely supportive of young scientists and women scientists. My first encounter with John was at the Women in Material Science Engineering breakfast at MRS. John looks very happy, surrounded by women scientists in this photo taken at ECS a few years ago. And John is always approachable, very generous with his time, advice, and knowledge. And sometimes even would break his good routine and good habits and stay up to have late dinner with a group of enthusiastic young scientists. I will start with John's advice to discover the next breakthrough. Develop your own scientific vision and voice, enjoy what you do, and believe the importance of your explorations. Be curious and ask questions. Challenge conventional thinking. Compete against problems, not people. Collaborate and have an open mind. I came to know John through our collaboration on electrocatalysis, catalyzing oxygen reduction and oxygen evolution. And this is a group of people whom I work with at MIT, Jean Santwich, PhD student in material science back then, and now professor at Cornell. Naoki Yabuchi, a postdoc, and now professor at Yokohama National University. Hubert Gastegger, visiting professor, and now professor at Technical University of Munich. We were looking at a series of perovskite oxides, and we're examining the catalytic activity for oxygen reduction and looking for a descriptor of activity for these oxides. Jean observed an interesting observation where the activity for oxygen reduction for these oxides exhibit a volcano trend as function of antibonding electron filling for the transition metal ions, namely EG electrons. And he proposed the following to explain this volcano trend, where the EG electrons can regulate the energetics between absorbates and then transition metal sites on the surface. Right? For oxygen reduction, essentially we need to go through a few reaction intermediates, oxygen, absorbed oxygen, OOH, O, and OH minus. For the left-hand side of the volcano, where the binding strength is strong, where generation of OH minus can be limiting. On the right-hand side of the volcano, the absorption strength is weak, where absorption of oxygen can be very limiting. We were very excited about this concept, but we're very afraid that this concept was, fundamentally flawed. So we had to check with someone who knows an oxide electronic structure. I recall approaching John with trepidation in a conference. John was very approachable and he listened. And that was incredible, right? Because I don't come across as a credible scientist. In fact, recently I had my 30-year high school graduation reunion in Beijing, China, where I came to connect with some of my high school classmates for the first time after 30 years. So, what are you doing in the US? I responded, teaching. Then my classmates followed teaching English. To our pleasant surprise, John largely agreed with this concept, but corrected that surface spin state for some transition metal ions can be significantly different from bulk, which is important to correct and consider for catalysis. Then we went on and also reported that EG electron filling can also govern the catalytic activity for water splitting. John is easy to work with as long as you can understand him and understand his handwriting. He's very dedicated to collaborations and dedicated to science. So this is one example of his early edits for this manuscript. Unfortunately, we were not able to utilize much of his edits for this paper due to the length and format requirement of this journal. John went along and didn't really say much about it. But since every time I would meet John in person, and John would gently mention this to me, Yang, you don't like my writing. The fact is not I don't like John's writing, it is very often my thinking is many, many years behind. I want to point out John's writing here. The dependence may be used as a guide to the identification of oxide catalysts having a Fermi energy pinned at the top of oxygen p bands for these reactions. Certainly back then, a decade ago, I didn't know what this meant, nor we had any experimental computational evidence in support of the statement. Only many years after, 6 or 7 years after, we were able to use DFT and X-ray absorption, X-ray emission spectroscopy to measure out the unoccupied states and the occupied state of metal and oxygen with a series of perovskites, where we can show as we lower the Fermi level into the oxygen p band, where we change and decrease the charge transfer energy of these oxide, we increase catalytic activity for oxygen evolution. And indeed, for these most active catalysts for water splitting, the Fermi level is pinned on top of the O2p band. In addition, we were able to show for these oxides with Fermi level pinned on top of O2p band, not only the metal sites can be active, but also surface oxygen site can be equally active for catalyzing water splitting and oxygen evolution. And more recently, we have extended this concept to understand electrolyte oxidation for positive electrode materials in lithium-ion batteries. So as we lower the Fermi level into the oxygen p band or into the ligand p band center, we decrease the driving force for oxidation of electrolyte solvent, where we have a solvent interfacing with a highly reactive oxide surface. And this driving force for this oxidation occurs by an oxidative dehydrogenation reaction, where EC molecule come to the surface and where we're able to strip a hydrogen from EC and generate a proton on surface oxygen, and the remaining fragment is absorbed on a nearby oxygen. And simultaneously, the surface metal ions are being reduced. And this oxidative dehydrogenation was supported directly through in situ FTIR measurements. As we charge NMC 811 above 4 volt, we see additional signals at a higher frequency to that of EC occurs. And this signal comes from vanillin carbonate. And we can form vanillin carbonate by stripping 2 hydrogen from EC and form a double bond. So utilizing this concept, if you want to design a stable surfaces with a minimum reactivity to oxidize electrolyte, then we will want to have surfaces with a very high Fermi level away from the ligand p band center to minimize electrolyte oxidation and increase the cycle life of batteries. So over the past decade, through collaboration with John, also being inspired through his work, that we have developed a unique scientific voice in using oxide electronic structure to design catalytic activity and interfacial reactivity, ranging from oxygen reduction, oxygen evolution in basic solution, to surface exchange kinetics at oxide-oxide interface, to oxidation of CO to CO2, the oxidation of NO to NO2, and of course, designing the oxide surfaces and organic molecules, these interactions for either minimize oxidation of electrolyte in lithium-ion batteries or designing selective oxidation of various fuels for chemical transformation. Beyond electronic structure, we have begun to study lattice dynamics and try to measure and compute phonon densive states and correlate the phonon band center with the barrier of ion migration. The work of Seiha Mui has shown if we lower the lithium phonon band center, it comes with a reduced barrier for lithium ion migration for a series of lithium conductors. Similar trend has shown also for sodium ion conductors in collaboration with Wolfgang Zayer. So these correlations beg the question, can we use the phonon band center of the mobile species as a descriptor to design ion mobility? And can we utilize this descriptor to predict new ionic compounds? Through collaboration with Johannes Vos at SLAC, we were able to screen and compute over 1,000 lithium-containing compounds in the inorganic database. And in particular, we're looking for compounds with low lithium phonon band center because we know it's correlated with reduced migration barrier. Coupling phonon densive states with electronic density states, we were able to predict 18 new ion conductors that should have a large band gap, also good ion conductivity. And some of these compounds were validated experimentally, exhibiting reasonably high ion conductivity. So this is one approach for some of us who might not have the physical intuition like John, who can directly report Nisicon, which is one of the pioneer compound for the sodium superconducting ion conductors. So the last example I want to show is where we began to combine oxide electronic structure and oxide lattice dynamics to understand what's the physical origin to design lattice oxygen redox. Lithium-rich transition metal oxide, pioneered by Mike Thackeray, provides greater discharge capacity than the stoichiometric layered compounds. And this extra capacity has been attributed to lattice oxygen redox. Like many other groups, such as Jean-Marie Tarascon, we also utilize lithium ruthenate, lithium-2, ruthenium-03 as a model system to understand what electronic signatures or features or phonon features that would enable more of the lattice oxygen redox and minimize oxygen loss or oxygen evolution, so we can increase the reversible lattice oxygen redox and increase discharge capacity. So if we have lattice oxygen redox or oxygen-oxygen coupling, we might expect the formation of the OO antibonding and bonding states, sigma and sigma star. And we did uncover unique spectra features related to oxygen-oxygen coupling in lithium ruthenate. In particular, shown on top, we have the ruthenium L X-ray absorption edge, where we see the increased intensity towards a higher photon energy. And this increased intensity can be attributed to the formation of the OO sigma star antibonding states hybridized with ruthenium-4D. In addition, there's a broadening in the X-ray emission spectroscopy of the oxygen K-edge, and this is as a result of the formation of OO sigma states due to the coupling. And these assignments has been confirmed and verified directly through a density functional theory calculation of these spectra using the ocean code. Beyond the electronic structure signature of OO coupling, we also observed a unique phonon spectra changes. Removing lithium from lithium ruthenate, we didn't see the creation of the characteristic frequency related to oxygen dimers, like what we see typically for lithium manganite, right? This signal around 1000. Instead, for lithium ruthenate, we see there is hardening of oxygen-oxygen stretching, and this indicative of a stronger oxygen-oxygen interactions within the oxide lattice. We propose that the hardening of oxygen phonon or oxygen-oxygen interactions facilitated by stronger metal-oxygen bonds is key to enable reversible lattice oxygen redox, as we have seen for uranium and ruthenium oxides. On the other hand, for lithium transition metal oxides with significant oxygen loss during charging, is accompanied with oxygen phonon softening and the formation of this oxygen dimers in solids, and eventually could lead to oxygen loss and during cycling and irreversible oxygen redox. So therefore, we want to design and find the structures or metal oxygen strong interactions to be able to stabilize the OO coupling within the solid matrix. So I want to end by coming back to John's advice. John, I want to thank you for inspiring us and encouraging us to develop our own scientific vision. And I want to thank you for encouraging us to challenge conventional thinking, compete against problem, and that people collaborate and have open mind. I want to add to John's list, and that is to eat more chocolates. Based on this highly cited article from New England Journal of Medicine, increasing chocolate consumption would increase the number of Nobel laureates per 10 million population. US is here, China is here. Clearly, if we want to do better science, we need to eat more chocolates. Considering the favorite candy in Texas is candy corn, I find it's quite remarkable that John went to Stockholm last year. Had John worked in Arizona, for example, and John probably would have won the Nobel Prize years earlier. Happy birthday, John, and thank you very much.
Okay, thank you so much, Professor Shao-Horn. Yeah, you share the impressive story with Professor Goodenough. As a postdoc or the students or professor, we also have the same experience. And he always, correct paper for us, and his handwriting is very special. So many people, they want to ask not an academic question, it's some the female scientists or the younger scientists. As Professor Goodenough, he always encourages the younger students or the female scientists. So could you please give some advices? Based on your experience, yeah.
I could say no more than what advice John has given. Develop one's own scientific voice And I think the journey is very important, and willing to try one's ideas and challenge conventional thinking and ask questions, collaborate to learn from others, and keep trying. I work hard.
Any more? Maybe ask Professor Goodenough. Yeah. Okay, thank you. Thanks again for your story and your contribution to our symposium. Thanks.
Thank you.
So now we come to the closing remarks.
Wonderful. So Professor Goodenough and Professor Manthiram are both here. Professor Goodenough, do you have any remarks at this point? I think we'd like to have some last words from you if you have. And please turn on the microphone.
Beginning. Start from the beginning.
I thank all the participants, speakers, the friends who sent me birthday wishes, and Wiley Publications for organizing this symposium on my 98th birthday. Thank you all.
Thank you. Thank you very much. Of course, I think it's the honor is ours to have been able to be present and help celebrate your birthday with you. So we very much appreciate it. Professor Manthiram, do you have any final?
Yes. So we made it. First, I thank Wiley Publishers, particularly John Wilrich, for making the 2 special issues and this symposium possible. Second, I thank all the speakers for their kindness to share their research perspectives on a Saturday instead of spending time with their families. Third, I thank Yunhui Huang for all his hard work with his students and working hard with John. Finally, I thank John for providing me the opportunity to work with him both at Oxford as well as at UT Austin, and for all the education and mentoring I received from him over the years. Apart from science, the best lesson I learned from John is be humble, be modest, be generous, and do not trumpet. Happy birthday to John again. Thank you.
Thank you, Ram. Thank you very much.
Thank you.
Professor Yunhui Huang, do you also have some words?
Okay. I mean, it's so exciting. I mean, again, happy birthday to Professor Goodenough, especially on behalf of all your students and postdocs. And the second, we are so appreciate, I mean, the invited speakers and all the attendees for their to the contribution of the symposium. And we also very greatly, I mean, appreciate Wiley, the team, for the organization and for publication of the special issue. Thank you all. Yeah, that's it. Thanks.
Oh, thank you, Professor Huang. So I'll just say from my end here, as we conclude, I'd like to thank certainly, first of all, Professor Goodenough. Again, thank you very much for being here. I think I would love to have the opportunity to do this again. It was a wonderful symposium and great to have you here with us. Thank you certainly to Professor Manthiram and to Professor Yunhui Huang. So they've done quite a lot to help us organize this symposium, as well as to organize the special issues that were a part of this. From behind the scenes, as well on the Wiley team, Dr. Muxian Shen, as well as Bo Yang, Dr. Dimitra Goku, Dr. Aaron Brown, Melanie Baumann, and Daniel Gonzalez have done a lot of things in the background, so they know what they've done. I appreciate, and I think we all appreciate the efforts in helping put this on. Thank you certainly to all of our invited speakers and to everyone for attending, both on Microsoft Teams as well as in Bilibili around the world. So with that, I'll conclude. Thank you so much for attending, and I hope to see you soon.